Hello, good morning to everyone. I'm happy to introduce Lou Pino. Mr. Lou Pino is the Research and Technology Development Lead of a company called InteraXon Inc., or it's also called Choose Muse. He has several decades of experience in developing a variety of technologies. He has worked in Waterloo and also consulted with food as well as instrumentation and other related industries. Today we are going to learn more about the technology behind Choose Muse. Please join me in welcoming Lou Pino.
Hi everyone. Thank you for the introduction. It's nice. So what I'm going to talk to you today is I'm going to give a background on Muse and its consumer application. So brought one here. And then a little bit of background on electrophysiology and EEG to tell you a little bit more about the instrument. And then the main topic of what I want to talk to you today is sort of like walk you through development process of a classifier that we built for the Muse. And the classifier predicts whether a segment, 1 second of EEG of the signal that we're picking up from the sensors is actually a brain signal or some contamination that, such as eye movement or muscle tension and that sort of thing. So that's the main topic, but I want to give you a little bit of a background before I get into the problem, the development problem that I'm going to go through. So Muse, it's a portable 4-channel EEG headset. In addition, it's got an accelerometer and gyroscope. And so what we've created is a clinical grade signal quality at a fraction of the price, right? So currently we have about 100 researchers, 100 research institutions around the world that are using Muse because it's portable and inexpensive and easy to use and set up, right? So I don't know if any of you have seen a traditional EEG system. So this is a full cap EEG system, and so it takes a technician like about half an hour or an hour to snap in all the electrodes and apply conductive gel and fiddle with the electrodes to get good signal quality. So, and these systems go for anywhere from 10,000 to 50,000 or even more, right? So the difference is I can do this, maybe require a little bit of adjustment of signal quality on a mobile phone, and I'm set up. So that's what I want to talk to you about in terms of how, the setup time for that to get signal quality versus the setup time for this to get signal quality. So this is a little more information on the Muse. So it has sensors in the front. The ears are conductive rubber. So we're actually getting 4 channels, and there's a reference in the center of the forehead, and then there's a DRL circuit which provides noise cancellation. So it's created to be comfortable and worn a long time, but also at good signal quality. And there's sort of there's tension. These are adjustable, and there's a little bit of spring tension to hold the headband in place. So here's a comparison of the Muse. So what we did was we took a full cap, and at the same time we stripped out. We just took all the plastic casing off of that and just put this flex band, and we're able to put the Muse underneath the cap. And we recorded in 2 places very close together, and we compared the signal that the Muse was getting to the signal of that very expensive full cap conductive gel EEG system. And you can see here that the Muse is red and the clinical grade is in blue, and you can see how well the two corresponded. In addition, Muse has like an auxiliary port, so you can plug in another lead, and you can get a stick-on electrode. And so what we did was we took a stick-on electrode and put it on a left collarbone, and that's a great place to pick up the heart rate. So here's an ECG, and we also did the same with the AccuChamp system, and compared, and they're very closely aligned. And this is another way of comparing signal quality by comparing how much power there is in terms of different exercises. And so this was compared to a different, this is a comparison of Muse to a different system called GTEC. So a little bit of the specs. I'm not going to talk about it unless there's questions afterwards. But basically, it's 256 hertz sampling rate. It's the most at a 12-bit resolution. So the electronics, there's the electrodes. There's the op amps and analog front end and amplify it. The tiny signal, and also the DRL circuit is in there. Then there's an analog to digital converter. Then we do some digital filtering, and then we send the digital signal across low energy Bluetooth to like a smartphone. So I want to talk about the application that we chose. So we wanted to sell the Muse to consumers, right? And so consumers aren't going to, need some really nice software. So what we developed is some really interesting software to address the issue of mental health, particularly stress and anxiety and depression. And so this chart just shows, on the left-hand side, shows the problem in terms of all the statistics, and these are statistics related to the United States, but they're very similar in other Western countries in terms of, 60 to 90% of all doctor visits are linked to some kind of stress-related illness. There's a high rate of anxiety and depression, and a huge economic impact on stress. So the remedy for that is showing up to be, a lot of evidence is showing up that mindfulness or meditation is showing up to be very effective as a way for people to help manage stress and help to be more self-aware, right? So in terms of the number of publications, this was 2011, and it's still exponentially growing in terms of how many academics are studying the benefits and the impact of mindfulness and meditation. So there's a lot of evidence that's showing it's very effective in terms of as a treatment for stress, depression, and anxiety, and training for attention and just emotional resilience. So we developed. So here's some proof that meditation is helpful. So this was a study done by Harvard using an MRI to measure the thickness of the insula and the prefrontal cortex, and the x-axis is age. And so as people age, the blue are people that meditate across their life, that are meditators, and the red are people that don't meditate. And as you can see, that there's a decline in thickness in cortical, in these important cortical areas. So meditation helps keep all of those dendritic branches bushy and thick. So here's some pictures of the app. So you can choose. We use weather as a metaphor for your mind. So you wear the Muse, and it sends the EEG to a phone, and then the phone gives you audio feedback using weather as a metaphor for your mind. So you're listening to your mind as a sort of weather, and that helps you. It's called neurofeedback, and that helps your brain realize, gives you reward signals to help you align your brain towards meditation. And then after your session is over, we give you some metrics that tell you how well you were doing during your practice to help you improve. So a little bit. So I want to move and talk about some things about physiology. So we want to measure your brain signal, right? But there's all kinds of things that are going to get in the way of us getting actual brain signal, because the brain signal is like microvolts. So plus, the typical range of brain signal that we're measuring at the scalp is like plus minus 30 microvolts. So it's very, very tiny voltages. And all kinds of things can get in the way. So, but before I talk about that, I want to talk about the origin of, where does the electrophysiology come from? So here's what an action potential is, and it's showing one neuron, right? So when a neuron depolarizes, right? So usually what happens is that some kind of channel opens, and there's a whole bunch of sodium ions on the outside of the neuron, and there's a whole bunch of potassium on the inside of the neurons, and some channel opens, and so a whole bunch of sodium just rushes into the inside of the neuron. That changes the potential at this point. And then beside this, there are voltage-gated channels that start to open, and this whole cascade starts happening of all these ka-ching, ka-ching, of all of these gates that open, and this wave propagates down. And as the wave propagates down, sodium ions go inside and potassium ions go outside, and it's these movement of ions that create this shape of voltage. So if you were to have a probe right outside this axon, this is what you would see. And what we're measuring at the scalp is the summation of tens of thousands of all of these neurons firing sort of in unison and in waves and in a pattern. So the summation of large amounts of neurons are what we're measuring at the scalp. So we can tell a lot from the EEG about your physiology. Here's an example from sleep research. So the top trace is showing you fully awake and relaxed. Then the next one is stage 1, which is drowsiness. So theta waves start to become prominent. And then stage 2, when you're sleeping, then we see sleep spindles and other signal formations called K-complex. And then when you're in deep sleep, you have usually more delta waves, which are stronger amplitude and low frequency. And then when you're doing REM or dream sleep, then you can see this kind of EEG signal. So EEG has a long history of being used for various studies, and sleep is one of the strongest areas that they look at. So there's a lot of frequency information in EEG. And so what delta is the slow-moving, high-amplitude wave, which is about between 0 and 4 hertz. Theta is like between 4 to 7 hertz. Alpha is about 7 to 13 hertz, and beta is 13 to 20. And so roughly speaking, delta is strongest during deep sleep. Theta is strongest during drowsiness. Alpha is strongest during when you're relaxed, and you're also doing inhibition control. So if you were, lining up to take a shot to do a free throw, and you were trying to block out the sound of the crowd, your alpha signal would increase, and that's a signature that you're trying to inhibit other sensory input. And then beta is strongest during active thinking and concentration. Okay, so that's a little bit of background on EEG. So I want to tell you about the problem that I'm going to speak about today, and give you some, hopefully a little introduction into some of the tools that you can use to analyze electrophysiological signals. So what we want to do is we want to know when we're actually getting brain signal or clean EEG, and we want to recognize those segments of the signal that are contaminated with eye movements or blinking or muscle contractions, right? Other contaminants are what we call electrode depolarization, sort of like there's a sudden flip in the charge on the electrode, which is kind of mysterious. And then if the person's moving and the electrode is sliding across the skin, that's going to cause signal degradation as well. And you also pick up the headband, and we'll pick up like environmental noise, electromagnetic noise like the AC power line. So the problem is we want to give accurate audio feedback to the user to help them guide them into meditation, and we don't want these sort of other contaminants in the signal to disrupt and create inaccuracies in the person's experience. So how we do it is using machine learning. So here on the left-hand side, I name the signal. So EOG is electrography, which is the electricity that your eyes create. So your eye is like a dipole. EMG is electromyography, so that's the electricity that's the measurement of electricity that your muscles produce. And EEG is the brain signal, and there's motion, and there's also sometimes even heartbeat. The ECG can contaminate and get all the way up to here, and you can see heartbeat as a contaminant in the signal. So what we do is we want to extract, so these are streams of data, time series data, and what we want to do is extract features from all of these to help us recognize when is this clean EEG versus when there's a contaminant in it. And so we look in the time domain, we look in terms of spatial features, in terms of where the signal is coming from, and we're also looking at frequency information. And as I introduced frequency, there's a lot of interesting information in the signal when you analyze the frequency components of the electrophysiological signal. Okay? Then, so basically, choosing the right features is the most important part of machine learning. If you get that right, then training a classifier with labeled data, labeling is can be challenging as well, but learning and training a classifier is easy once you've got the features selected correctly. And what I mean by traditional machine learning is that you need a domain expert that understands what these signals mean and can identify them by eye and sort of help find a whole bunch of segments of what are labeled data to tell the classifier, yes, this is a segment of eye movement, and this is a segment of clean data. And that labeling process allows the statistics to categorize all of the features or the variables that have been measured to train a classifier. So I'm going to this is a quick introduction, so I'm going to get into a little more detail in terms of especially these two parts and a little bit on the learning and training. So your eye is like this big battery, and when you move it, it creates this voltage that is measured on your skin. And when you blink, you'll also see a similar signal. So blink is like about 300 microvolts peak to peak for when we measure it with our electrodes. And a blink and a typical eye movement is about 300 milliseconds, like a saccade. Is about a blink lasts for about 300 milliseconds, and most isocads are in that range. So in muscles, so the muscle itself is another muscle fiber is similar to a neuron in that it'll propagate an action potential in the same way. So muscles will create a lot of electricity from very, very subtle, small voltages to very, like a jaw clench will produce a very strong muscle signal and it's a very high frequency signal. So here's a heart signal. So I guess about on average 1 second the heart will beat, and you can see the typical QRS wave of the heartbeat. And that sometimes happens, not often. It depends upon the person and their neck and various other factors. And motion, right? So then we have like an accelerometer and a gyroscope in the muse as well. So I'm gonna talk about a little bit more about feature extraction. So time domain, spatial features and frequency features of the raw signals. So this is a spectrogram, and so what a spectrogram is. So here's the 4 channels of the muse: 1, 2, 3, and 4. And the x-axis is like a 1 second slice of time. All right. So let's start here at 0. So this is the first second, and at that first second, this is the power of each frequency component. So the y-axis is frequency. So if you pick a pixel here, and let's say at 50 hertz, that color represents the power of the frequency component of 50 hertz in that signal at that moment in time. So you can decompose a signal all the way across. So this is like, how many seconds is that? I can't read it. But anyway, that's a few minutes of data there, right? And so at each point, at each second, you can see, well, what are the frequency components that comprise that signal? So here in the early stages here, there's a lot of energy here because yellow is showing higher power, and blue is lower power. So here it looks like the person was fiddling with the headband to try to get it on, and that's creating a lot of power in the signal. And here at 60 hertz, there's a blue line all the way across for most of the signals. And so any ideas of what that could be in terms of what's happening there? In terms of that pattern?
Just like an oscillator with all the 60 hertz noise?
Yeah, that's exactly it. Yeah. And then here in channel 2, it looks like there's a lot of energy all the way across, and I would say that electrode just never got connected to the skin, and it's just oscillating wildly from one rail to another, and there's a lot of power in that signal, but it's not brain signal. So this is a good example of how to just get a picture of what's going on. So another way of getting information from, like, we have 4 electrodes, and so they're placed like above the ears, and left and right forehead. And so this is a topographical representation of a wink, right? So there's a lot of red is stronger here, and blue is lower voltage. And so just using the 4 electrodes of the muse, this and plotting like using isolinear lines, the voltages, you can see that there's a lot of voltage coming from the right eye where the wink was. So we can use math techniques like common spatial pattern or coherence or correlation or different source localization techniques to sort of what is the pattern of EEG that's coming out of the brain. Like, is there some source of strong 10 hertz energy coming from one part of the brain, and that may be useful for us in terms of classifying and getting information about the brain. So this slide is talking about spatial features. So then another, this is the time domain. So here's a signal that I took from our database, a segment from one electrode. And so we can get time information from the EEG signal. And usually we look at like amplitude or variance or kurtosis or other complexity measures like entropy or mutual information. So what I'm going to do, look at this signal, and I'll call it that signal segment number 1, and it looks like there's a lot of, in my eye, it looks like there's eye movement happening there. And segment 2 looks like mostly clean EEG, right? It's hard to get 100% clean, but so segment 1 is it's really not clean. So I'm gonna analyze these 2 segments and see what we can find out about them. So the first one, which is the clean segment. So this is the spectrum. So I showed you a spectrogram, which is at every point in time, what's the energy at each frequency bin in the signal. So this is like this is the spectrum across segment 2. So I added up all of the power across that entire segment, 1 second at a time, and took the mean. And this is the mean power of each frequency in segment 2. So you recall segment 2 is this one. So I did a frequency decomposition. So what's at each frequency in segment 2, how much power is in that frequency? And then I plotted it here. So you can see that delta is the low frequency is strongest, and then it tails down. So most of the energy in the brain signal is in about 0 to 40 hertz. There's some papers that say that we can get energy higher than that, but it's really hard to distinguish it from background muscle noise. And so muscle noise will go from 20 hertz, even lower, all the way up to 100 hertz. And here you can see that that's a 60 hertz notch filter that we applied in the headband to remove AC noise. So typically EEG has this curve. In terms of the spectrum of EEG, has this curve that goes 1 over F with respect to the log of the power, right? So that, if you see that shape, that's good indication that you're actually seeing some brain signal, but it's not a guarantee. So that was segment 2. Now, so I want you to pay attention to the difference between segment 2 and segment 1. So what we're seeing in segment 1 is this huge jump, right? And so this is log, right? So one unit jump is like 10 times in power. So here we're peaking out at around 1.5 decibels, and sorry, log 10. So that would be bells. So 1.5 bells. And here we're peaking out at 3. So there's a huge increase in low frequency power. So that's an indication that, well, that's likely the contribution from the eye movement to all of that low energy power, because eye movement is slow relative to brain signal. So you'll see that this is the signature frequency of eye movement. So another thing that we can do is just take each voltage value and just plot a histogram of it. So we'll divide, the x-axis is in microvolts, and that sample is 100 microvolts, so we add it to the count over here, et cetera. So for each voltage sample in that segment, we'll add it to this histogram. And so what we see is typically what we'll see in EEG is this shape, and this green dashed line is an estimation of what the probability density function of this histogram. So does that look familiar to you in terms of what kind of probability distribution function do you think that is? So that
like you're saying, what function does that look like?
Yeah.
Like a Gaussian?
Yeah, that's a Gaussian. So clean EEG, the voltage values, if you plot them in a histogram, will have a nice Gaussian distribution. But what's interesting here is that there's thicker tails. They didn't turn out to be as thick as I wanted them to for this illustration, but but you can see that there's a lot of voltage values that are outliers, and so kurtosis is a measurement of how thick your outlier tails are. So this suggests that maybe we can use kurtosis as a way of measuring, is this clean EEG or is there some kind of contaminating artifact in it?
Sorry, I have a question.
Sure.
Just I see that your voltage is from, like, I think it's -300 to about like +300. So is that like the blinking that you'll see then?
Yeah.
So at the end, that's your blinking, like the peak to peak? Okay.
Yeah, well, the blink will have a strong negative voltage, the way our electrodes are configured and located. That's right. So amplitude so this suggests that amplitude and kurtosis are good candidates for features that we want to look at. So this one I took from a very good paper on muscle contamination in the EEG signal. So this was measured at AF7, which is this electrode location here, the left forehead. So this dashed line is the spectrum of the person contracting their frontalis muscle at about 15% of its maximum contraction. And you can see that there's a lot of high frequency power in that contraction compared to the solid line, which is the frequency spectrum of that person at rest, right? So this is another, when we're trying to decompose or high frequencies above, especially above like 20 hertz or whatever, are good ways of finding muscle noise. Okay, so again, that same segment, the same EEG signal, and so I took kurtosis and I calculated. So I divided this signal up into 1 second epochs, and I made them overlapping. a little bit so that I could get more information that way if they're overlapping. And down, the blue plot is kurtosis, and it shows for each of those 1 second epochs, what's the value of kurtosis for each of those 1 second intervals. And the red is, I took the variance of the signal, because variance is also, the units that variance will return are microvolts squared. So it's actually variance and power are the same thing. So just by calculating the variance of the signal, we'll get the power as well. And then I took the log of it, so that the log will just give it a nice bound and a range, so that this won't have too high of a peak. So I calculated kurtosis and log variance of this signal, and so we can sort of see that there's a lot more peaks of kurtosis, and high value kurtosis means that there's thicker tails in the distribution of those voltage values. And higher values of variance means that there's more power in the signal. So we can see here that in segment 2, the variance of the power of that signal is lower compared to segment 1. And there's also more spikes, like in terms of kurtosis here. But it looks like it's more sporadic and more hit and miss in terms of kurtosis. So it looks like log variance looks like it's a more reliable feature of measuring whether this a clean versus contaminated EEG. So we want to build a classifier. So we've collected some features, right? So when we did this, we collected a lot more, but I'm not going to go through all of the features in one class. I just want to check the time. So here's a simple way of making a classifier for one feature is, well, let's just build a histogram. So the pink is the segment number 1, which is the eye movement. And the black is the histogram for the clean segment, right? So if we just pick the threshold here and say anything to the left of this, we'll classify that as clean signal, and anything to the right of that we'll classify as contaminated signal, and we'll use these histograms as the ground truth. How well would this classifier work if we build this simple classifier? And the way of estimating that is, well, if we're saying that if our prediction is anything to the right of this line is contaminated signal, yet we're seeing clean signal, so we take all of the counts of clean signal that were misclassified or error and divide that by the count of the ones that were correctly classified. That is your classification error for clean signal. And similarly, so everything to the right of that line, we're classifying it as contaminated or signal. So all of this pink was classified correctly, but then the error that was misclassified is to the left of that. So we take the count of that and divide it. We take the total counts here and divide it by the total count to get what the classification error rate would be for bad signal. So as we can see, this is not a very good classifier, right? It's got a higher error. It's got a high error rate. So can we do better? So let's look at variance, right? So if we choose this threshold, and we can, you can choose the threshold by moving it around and optimizing it so you get the maximum accuracy, right? So you change the threshold, and you find, and there's other mathematical ways of doing it, like minimum Euclidean distance, which I'm not going to get into. But again, you can choose the threshold here and say everything to the right of that threshold that has log variance greater than this, we'll classify that as bad signal. Everything to the left of that, we'll classify it as clean signal. And then you can look at the tail here and the tail here, and and see that this is not bad, right? The error rate here is pretty decent. But can we do better? So that was looking, let's build a classifier looking at one feature at a time. Well, the actual way to do it is to combine features and look at them simultaneously. And so this is an actual plot of real data. I've added a third category, but just focus on the green and the blue for now. And so for each second of EEG data shows up as 1 point, and you plot each of those points in terms of what's the log variance at that second, at that 1 second of EEG, and what's the kurtosis of that 1 second of EEG, and you do that for every plot. And since I've labeled it, I know whether it's green. I've given it labeled training data, which is ground truth. So I've labeled it, and so you can see how contaminated EEG scatters in the shape of it, and green EEG it is shaped. So this is a scatter plot, and it's a good way of visualizing what the data looks like in 2 dimensions. And you can usually do it for 2 features at a time quite well. You can do it for 3, but it gets harder to see it when plotting. And so usually I use MATLAB as my tool of choice, but here's an example of a free tool called Weka that's available for doing machine learning. So any questions on? So
can we be able to do the classification using artificial neural networks rather than machine learning? What is the unique advantage of going with machine learning than ANN?
Okay, so artificial neural networks are a type of machine learning, but I think what you're getting to is, so the big topic today in machine learning is called deep learning. And so what I've been talking about is traditional machine learning, right? So I didn't mean I can get into that in more detail. I think I'm going to just talk about a few more things. I think or should I? We have time. Okay. So you can take that scatter plot and look at it, and you can use. There's a whole bunch of methods that can just draw mathematically. You just feed that method in Weka or MATLAB, and it'll find a linear boundary between your different classes that will optimize your classification error, right? And so there's many examples like distant regression, or a vector machine, or single perceptron, which is artificial neural network, can do this, or linear discriminant analysis. I'm not going to go into the math of these because I'm not have time. Another way of doing it is using nonlinear methods, right? So multi-layer perceptrons, or support vector machines with nonlinear kernels, or decision tree, or nearest neighbor. And so what can happen there is that you get a nonlinear boundary that separates your data, and this looks like you're getting 100% accuracy for this training data, but is this a good idea? Well, why not?
So your points are going to be in different places when you do a different trial.
Yeah. So it's not generalizable. You give it a different setup. You give it data it's not seen before, and its misclassification rate is going to go sky high, or much higher. So it's not necessarily a good way of doing it. So the thing to do is to try to choose a method and keep testing it for accuracy, and withhold test data so that training the classifier that the data that you use to train the classifier doesn't see the test data, and then that's how you test to see if your classifier is working well. And you want to choose the simplest model you can. And so to get back to your question, so deep learning, if you have lots of data and you've got lots of computing power, it will learn the features, right? Whereas what I've been telling you today is you need an expert with domain knowledge, what the signals mean, to help build a classifier, to choose what are the best features to choose, or another way is just keep throwing features at it until you find ones that work well. So the difference, deep learning, which is basically using large stacks of artificial neural networks in a number of perceptrons or artificial neurons in each layer, and if just continually training that and changing the weights through that by training it and minimizing error, that's where all of the big companies are spending all of their money right now, because deep learning is the hottest topic. So you need a lot of data, you need a lot of computing power, but right now, deep learning is the state of the art, because you don't need a domain expert. The method will learn the features. And so I don't think I have enough time to talk about independent component analysis, but here's an example of deep learning. So here's in this paper on sleep stage classification. And so you can see that it's picking out interesting features. So here's some sleep spindles and K complexes. So it's actually, without it knowing anything about sleep spindle or K complex or any of these interesting features of sleep, deep learning was able to pick out interesting features. So I think I want to end it there and just open it up to questions. Did I answer your question? Yeah.
I have a question. When you're placing these electrodes, I noticed that the Muse just has the one band that goes across the front, whereas with the larger electrode helmet, you can put electrodes basically wherever you want. Can you reposition the Muse if you want to look at different parts of the brain?
No. It's meant to look at the forehead and hook over the ears. That's the way it was designed. That's the way it'll fit snugly and securely. The electrodes here are not designed to go through hair.
Okay.
Right. There is an auxiliary electrode. Oh, and by the way, there is, if you're looking for projects to do, there is a software development kit that comes for free if you buy the Muse, and you can. So a lot of students are using Muse for their research or various projects. Right. So if you wanted to get access to CZ, which is the center, or PZ, which is a popular place, you can add an electrode to micro USB port in the back, and with a stick-on electrode, and get access to it. Yes.
What's the price difference between the Muse and the regular?
So this one is $249, and so a full cap system with amplifiers and batteries, and anywhere from $10,000, $20,000, $30,000, depending upon how many electrodes and how fancy the electrodes are. Like the one we have a full cap system back in the office, and the electrodes light up like a Christmas tree, red, green, and yellow, to tell you which one is getting good signal. Do you have any? In terms of your classes, have you been taught machine learning, or statistics in terms of your coursework?
Taken a statistics course, but not machine learning.
Okay. Yeah. So I guess the hot topic is deep learning. There's U of T has a lot of expertise in it. I think a lot of other people are, but it needs a lot of data and graphical processor units, which are you know, you need a lot of iron to run the algorithm to learn it, because it takes a lot of iterations.
Yeah, we have a grad course software called machine learning. It's a grad level course.
Okay. Cool.
Any other burning questions or amusing questions? See, none. Let's give a big round of applause for this.